Good afternoon, students. Now it's our time to turn our aim towards the random process. As we have discussed so many things with respect to single random variables and multiple random variables, now we are going to see the random process. So, before going to start with the random process, first we will see something about random signals. We have learned how to analyze the signal at a particular instant of time. But now we have to learn to put across all the entire chain of random variables and analyze them informally. So that means more complexities are going to await for us, and we will form the concepts based on the random signals and random processes. Therefore, you should be quite comfortable through with all the previous concepts what we have discussed. Now, with this beginning, we start our journey into the world of random signals and random processes. Fine. So, what we will try to understand before we jump into the standard definitions, as especially autocovariance functions, autocorrelation functions, and so many things. But first, let us now understand the random signal and what is the random process and its other subcategories are related to those things as no sense stationary, strict stationary, weak stationary, and ergodicity. Before going to this all, we need to study something about random signals, and later we can study about its ubiquitic measures and autocovariance and autocorrelation, so many things. So first we will recap our basics as looking towards the random signals. The random signals, as we observe, have so many components which cannot be explained by known causes, or sometimes the causes are also unknown. So there are two distinct points what we have discussed in previous classes, that when you look at the measurements of those random signals are made up of deterministic inputs plus the components that cannot be explained by any features. Or sometimes I can explain you the known effects, or I have to relay the history of probability. So before going to this, keeping in mind all these concepts, the measurements of random signals entirely contains random effects. The random effects means these are time series modeling signals, or these are also called as stochastic signals. So according to this, we have categorized those random signals into two types, that is random effect signals and composite signals. So please note 2 points. First one is entirely contains random effects. Second one, composite signals. Composite signals means those are exogenous effects plus randomness. This is also called as system identification. Next, the definition. The definition of random signal is given by: a random signal is a function x of k, small x in bracket or square brackets k, whose characteristics cannot be accurately described by any existing mathematical functions, at which or at each point it is characterized by a probability distribution function. It means that the random signal or the random process cannot be only mathematically described or cannot be only mathematically modeled, but also it has to go through the probability distribution laws. Next, the random signals are viewed in two parts. One is prediction viewpoint, second one is knowledge viewpoint. Signal is not accurately predictable. This comes under prediction viewpoint. Second one is signal is always known with some errors or uncertainty. It means that according to our knowledge point of view, the signal is always known with some errors, means it contains some of the distortions, noise or errors. So one more definition for random signal is given by a random signal is an indexed ordered sequence of random variables in temporal, or we call it as also as time domain or spatial or frequency domain. First off, its characteristics can be described by probabilistic laws and not merely by mathematical models. As I said previously only, the mathematical models alone cannot help for the analysis of random signals, but it also has to go under probabilistic laws. What I mean to say is, if we consider x as a random signal, it contains all the values as x of k. The k may take any values from 0 to n. That is, x is equal to, open the flower bracket, x of 1 comma x of 2 till x of k, next x of k plus 1, x of k plus 2, etc. So when we say the random signals contains the random variables x of k, we can consider a thread of time or a timeline axis which hangs all the x of k variables. That is, x of k, if you say at any point, the forwarding is x of k plus 1, the preceding is x of k minus 1, and the time axis goes. So according to this, when we know all the things about random signals, there are some implications about random signals. A random signal cannot be predicted accurately. As the definition says, the first point, a random signal cannot be predicted accurately. Then the second point, at any instant, the observed value is one of the many possible values. Means x of k can take any value from 0 to n. So hence we can model our random signal or random variable or a random process as a two-dimensional factor. That is, one is along with the time axis, one is along with the outcome axis. Or the outcome axis can also be said as the amplitudes. Hence, as x of k is a thread having the timeline axis and all the x of k's are hanging along the timeline axis, the outcomes and timeline axis will contribute or will model the two-dimensional function of a random signal. Now, when you have seen this much about the random signals, we will next go to random process. The conventional definition for random process is: the random process is the ensemble of the random signals x of k, that is, it is the collection of all the possible realization of x of k. Means a random process is a two-dimensional function x in square brackets k comma omega. Here, in so many cases, we represent omega for the outcomes, but here it is represented for the frequency. Anyway, we are going to take the timeline axis. We can neglect the omega frequency component and we can just say it as x of k, which is in bigger brackets. So sometimes it may be also represented as v of k or simply x of k or any other variable p of k, s of k, anything. Next, we will see the signal which is shown in the figure x1 of t, x2 of t, x3 of t. This is the ensemble of noise recordings which is outcome of a random process. So now we conclude that any random signal which is generated from a random process is a collection of all the signals which are from random process. The process is nothing but a system which generates the so many number of signals. Hence, the collective or the collective ensemble of all the possible x of k will form the random process. Next, so knowing all these things, next we have to go to the probability density functions of random processes. So before going to this, we have to realize some of the characteristics of random process. Those are stationarity, independence, expectations, and correlations, autocorrelations, covariance. So all these things we will discuss in our next lecture. So thank you all.